Good evening, everybody. Welcome to Chem 1211 with your host, me, Dr. White. Tonight, I'll be doing a review for quiz number 3. And if you look in Blackboard, back on October 28th, and you received the email, this Thursday, I will be giving quiz number 3 online. At 8 a.m. or earlier, I will be emailing you the password for quiz 3 PDF file. You'll have until Friday, 8 p.m. Take quiz 3 and upload your answers to quiz 3 as a single PDF file. And I reserve the right to subtract 25 points, up to 25 points for anybody who doesn't follow instructions or doesn't upload your quiz on time, unless you contact me earlier in case there's something that came up. Quiz 3 has 4 pages, 8 problems. It's worth 50 points. However, there's 5 bonus points. The whole thing adds up to 55. You pick which one you want to call bonus. I don't. Now, it will cover Chapter 11, gases. And as you know, by the end of the week, I will have, by Sunday or earlier, I'll have the scores for quiz 3 and Blackboard. And I'll also send you an individual email for each points you got on quiz 3. Now, if you go to the lecture section of Blackboard, you'll find a file called Important Information, Quiz 3. And this will be the last page of Quiz 3. And you don't have to memorize these formulas. Oops, wrong thing. Right thing. Now, let's go through the review for test. Actually, it should be quiz here. Let's see something. Yeah, that should have been quiz right here. Sorry about that. Before COVID, this would be test 3, and there was other stuff in here. I forgot to change that. But anyways, the file in the lecture section of Blackboard, Chem 1211 Quiz 3 Review, which you're seeing. Now, when we talk about gases, an important thing is things you can measure. And one of the important things about a gas is the pressure. And this should be changed. I know in the quiz it's right here. 1 millimeter mercury equals 1 torr. 760 millimeter torr mercury, Hg is mercury, equals 760 millimeters of mercury, equal 1 atmosphere. And this right here is a definition. Therefore, 760 and 1 are exact numbers. Same thing up here. And if we look at Chapter 11, practice problems, which is in Blackboard under practice problem answers, you'll see I have some questions. Now, let me remind you, underneath your name in quiz 3, it will say, please use proper significant figures for all calculated answers. And it'll also say, please use 3 significant figures for all atomic masses. If you don't, I'll take off a point like I did in test number 1. Now, let's look at number 1. How many torr is 41.5 millimeters of mercury? We're trying to find torr. We're given millimeters of mercury. Here's what I start with. Here's what I'm trying to get to. And use your good buddy, your good friend, unit analysis. If you could have a conversion factor, what goes on top? Torr. What goes underneath? Millimeters of mercury. Where do you get these numbers? Important information, quiz 3. Remember, I changed the test to quiz. That's 1-to-1, which is why I have 1 and 1, therefore it's the same answer. Now, let's look at number 4. How many torr is 1.237 atmospheres? We're trying to find torr. We're given atmospheres. Here is the atmospheres. We're trying to get to torr. If I had a ratio to convert it, use unit analysis, torr goes on top. What we're trying to get to units, atmospheres goes underneath. And where do I find a relationship of atmospheres to torr? Right here. 760 torr equal 1 atmosphere. That's a definition. That means 760 and 1 are both exact numbers. So on top, I have 760 torr. Here I have 1 atmosphere. Now, do the math. And how many significant figures should your answer be? Well, this number, 1.237, has 4 significant figures. 760 and atmosphere are exact numbers, which don't play a role in the calculation of how many significant figures. This is the only number. When you multiply and divide, you get the same number of significant figures as the number you're multiplying and dividing that has the lowest significant figures. In this case, 4, and my answer is 4. Now up here in problem 3, 741, 3 significant. That's why my answer is 3, because 1 and 760 are exact numbers. All right, now you're going to need this later. How to convert from degrees C to Kelvin, you add 273. Now I talked about the gas laws, and these were laws that help scientists understand relationship between certain parameters of a gas. And the first one is Boyle's law. And Boyle's law is P1 times V1 equals P2 times V2. P1 is the initial pressure. V1 is the initial volume. P2 is the final pressure. V2 is the final volume. I'll never ask you what is Boyle's law, but I'll expect you to know how to use it and when to use it. And let's take a look at an example of that. And if we look at number 6, if a balloon has a pressure of 658 torr and a volume of 1.894 liters, what is the pressure of the balloon if the volume is increased, or if the volume is, it should be increased. I forgot the D. All right, don't look. But anyways, the volume is increased to 5.113 liters. Now, what are we being asked to find? A pressure, but it's not the initial pressure, 658. It's after you change something. So that's a final pressure, P2. If a balloon has a pressure of 658 torr, that's the initial pressure, P1. The initial volume is 1.894 liters. L is liters. And finally, the volume is increased to something, 5.133. That's the final volume, V2. And when you see a problem like this with only pressure and volume, then you know you need to use Boyle's law. P1 times V1 equals P2 times V2. Now, what are we trying to solve for? We want P2 alone on one side. Well, when you have two things multiplied, to get rid of one of them, you divide by that. Anything divided by itself is number one, which means it's gone. However, whatever you do to one side, divide by V2, you have to do to the other, which I did. Now, V2 over V2 equals number one times P2 is P2. And on this side, you have P1 times V1 over V2. Now, you don't have to do it, but I like to. I rewrote this where you have P2 equals P1, V1 over V2. Now, we took the time to figure out what is P1, V1, and V2. P1, I'll put in 658 torr. V1, 1.894 liters. And V2, 5.133 liters. Now, you do the math. And remember, in a multiplication division, you get the same number of significant figures as the number with the fewest significant figures. 658 is 3, 1.894 is 4, 5.133 is 4. In multiplication division, you get the same number of significant figures as the number with the lowest, 3. And there you are. And I have some more problems like that. You can look, and there's the same philosophy using P1, V1 times equal P2 times V2 and solve for either P2 or V2. Now, in the lecture, I talked briefly about Charles' law, which is temperature and volume. And most people get that wrong, so I don't put that on a quiz or test anymore. So that's my gift to you. Charles' law won't be on quiz number 3. But next, my favorite mathematical formula in chemistry is the ideal gas law. PV equal nRT. P is pressure. V is volume. N is moles. R is the universal gas law constant for this class, 0.0821 atmosphere liters per mole K. And T is temperature. Now, when you use PV equal nRT, it's important to know each of these has to be in the right units. Pressure has to be in atmospheres. Volume has to be in liters. Number of N is the number of moles, and temperature has to be in Kelvin. Now, I've yet to see a gauge that measures pressure in atmosphere, but I have seen it in torr and millimeters of mercury. So you're going to have to convert pressure to atmosphere, which we just did earlier. I'll always give you the volume if that's what you're given in liters. That's my gift to you. I've never seen anything that measures moles, but I can measure weight, grams. And remember from test 1, you should know how to do this. The mole, 1 mole of a compound equals the molecular weight of the compound, and the molecular weight of the compound is the sum of all atomic weights. Finally, temperature is always in Kelvin, but I've never seen a thermometer in Kelvin. But degrees C, yes. And you'll need to know how to convert degrees C to Kelvin using this formula, which you used for, I believe it was quiz 1 or 2. Just check and make sure you're seeing the right screen. Sometimes Zoom plays games. All right, let's look at number 10. Let's have some fun with the ideal gas law. If you burp 86.75 grams of carbon dioxide, most of your burp is CO2, at 540 millimeters of mercury and 34.6 degrees C, then what is the volume of your burp? But you never thought I can get into burps in my class. I do. So what are we trying to find? A volume. We're given a weight of CO2, the pressure, the temperature, and then you will be given R. Let me just show you. If you look at important information, quiz 3, you see here I give you the value of R. And I also am nice enough to tell you what temperature, pressure units should be in. Moles is N, temperature should be in Kelvin. So when you look at this problem right here, is anything changing? No. It's dealing with a gas. Therefore, we're trying to find volume and nothing is changing. That tells you should use PV equal nRT. And here I have PV equal nRT. I want volume, so to solve for it, I want it alone on one side. So how do I get rid of pressure? Anything divided by itself becomes the number 1. 1 times V is V. But whatever you do to one side, divide by pressure P, you have to do to the other. This cancels out. I'm left to V equal nRT. Now, pressure has to be in atmospheres. Oh, no, he gave it to us in millimeters of mercury. So we have millimeters of mercury. We want to get the atmospheres. It's time to use your good buddy, your good friend, unit analysis. You can convert it in one step. What goes on top of the ratio? Atmospheres, the units we're trying to get rid of. What goes underneath? Millimeters of mercury. And if you remember from the problem we did earlier, in important information, let me just show it to you. Right here, 760 millimeters of mercury equals 1 atmosphere. So on top goes 1 atmosphere, underneath goes 760. This is an exact number, 1 and 760, 3 significant, 3 significant. Now, in this type of problem, when you do multiple calculations, there's 2 philosophies. One is round off for each calculation, and Dr. White is a round off at each calculation. The other is round off at the end. For my quiz, I calculate both ways, and if there's a difference, you could have 2 separate answers. In this case, it's not. All right, so we have the pressure in the proper units. Next, temperature, degrees C. Nope, you can't use temperature as degrees C in this formula. It has to be in Kelvin. And temperature in Kelvin equals degrees C plus 273 And here we add 273 and we get this. Remember, when you add, you get the same number of significant figures to the right of the decimal as the number with the fewest significant figures to the right of the decimal, but exact numbers you ignore. So this has 1, and that's why it has 1. I shouldn't really have 4 significant, it should be 1 to the right of the decimal. Finally, when we look at this, we have pressure, temperature, we're given R. Now we need N, moles, but we're given grams. So now you have to take grams of CO2 and convert it to moles of CO2. Hopefully you learned this for test 1. We use a ratio. What goes on top of the ratio? Moles of CO2. What goes underneath? Grams of CO2. And right here, we have 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of the compound is the sum of all atomic weights. So what's the molecular weight of CO2? 1 carbon, 2 oxygen. If you look at, let me open it up, I didn't. Let me remind you, the number underneath the chemical symbol, in case of carbon, 12.011 is the atomic weight for carbon. And under your name, we'll say, please use all atomic weights, the 3 significant figures, and that would be 12.0. Excuse me. For oxygen, 15.999 rounds off the 3 significant figures, 16.0. And therefore, 12, 1 times 12 is 12, 12.0, 2 times 16.0 is 32.0. Add them up, 1 significant figure to the right of decimal 1. So the molecular weight of CO2 is 44.0. And 1 mole, 44.0, 4 significant, exact number 1, 3 significant, 3 significant figures. So now we have N. Now from PV equal nRT, we can put in N, we can put in R, we can put in the temperature right here, then the pressure in atmospheres. Common mistake using this type of problem, students put into pressure in millimeters or torr, or mercury or torr. No, you have to convert it to atmospheres. And for this problem, and I just picked a wild number of 86.75 grams, you'd have 69.4 liters of CO2 when you burp. Your lungs aren't that big. That would be almost the size of 70 2-liter bottles of gas. Nope, your lungs aren't that big. That'd be one hell of a burp. And notice I have both ways. Now, this problem 10, there's one thing I forgot to put there. What's that? 15 points, like I said in my lecture. Problem like this is a lot of work, so therefore it's worth 15 points. A lot of work. and open something I thought I had open. Now, before we leave P vehicle and RT, and the ideal gas law, P vehicle and RT, tells you when to check your car tires. Your car tires are gas under pressure inside your tires, and it follows P vehicle and RT. And if you watched the video, which I hope you all did, my story, what happened to me in one very cold winter. In winter, the temperature gets real cold. And that winter, the overnight temperature got down to about minus 25 Fahrenheit. That's not the wind chill, that's the actual temperature. And when I got up next morning, this is when I lived in an apartment complex and I parked outside in a parking lot. The morning temperature was still like 18 below. It was cold. And I figured I better go out and run my car around because the battery needs to get powered up. Batteries are affected by temperature too. But when I got out there to my car, I looked and I said, oh no, 4 flat tires. Took me about 2 seconds and I said, come on, PV equal NRT. And what happened was in your tires, the volume doesn't change unless you get a flat, but it doesn't change. The moles don't change. And the ideal gas law count, the universal gas law counts doesn't change. So if these stay the same, if the temperature goes down on this side, the only thing that will change is the pressure went down. So in the winter, when the temperature goes way down, the pressure in your car tires goes way down. I went out, started my car, got in, went to the nearest gas station, which was about 2 blocks away from where I lived. Back then, air was still free. Nobody was there yet. I was filling my all 4 tires with air. By the time I finished, which was only about 5-6 minutes, maybe less, there were like 8 or 9 cars in a line waiting for me to finish because P vehicle and RT tires went down. Now in the summer, what happens? It gets hot and the temperature goes way up. And one summer in 1995, we went almost 2 weeks where the daytime temperature was higher than 100. It was bad. About 600 people died from heat stroke. And since then, Chicagoland area, they now have cooling places when the temperature gets brutally hot for people to cool off and not die of heat stroke. But the same thing, PV and RT. In your car, the volume, moles, and the universal gas law constant stays the same. So if the temperature goes up, the pressure in your car tire goes up. And when I was driving home back then, I lived in Schaumburg and I worked in east, about 5 minutes east of Great America in Gurnee. So I had to take Toll Road, a long commute back home. In the afternoon, coming home on the toll road, you'd see cars and trucks pull over with blowouts. The pressure had gotten so high in their tires, like a balloon filled up so much, boom. And I knew better, and I kept a check on my car tires where I had to let some of the air out. Otherwise, it would go boom. That's PV equal NRT. And the last couple of things I like to talk about are Dalton's law of partial pressure. And that is the total pressure is the sum of the partial pressures of a mixture of gases. And here, P total is the total pressure, and P1, 2, 3, and 4 are the partial pressures of each gas in that mixture. And partial pressure means, and I'll never ask you what is partial pressure, but you should understand it. That's the pressure of the gas if it were alone instead of in a mixture. What would be that pressure? Huh. Well, I don't have any practice problems with that, but if you had All right, let's take a look at this problem. What is the total pressure of a mixture of oxygen gas, O2, at a partial pressure of 121 torr and nitrogen at a partial pressure of 321 torr? As soon as you see the words partial pressure, you know you have Dalton's law of partial pressures. The total pressure equals the sum of the partial pressures, P1, P2, P3, whatever. So what are we trying to find? What are we given? Partial pressure of oxygen, PO2, 121. And the partial pressure of nitrogen gas, N2, is 321 torr. And therefore, P total is the sum of the partial pressures, which are partial pressure oxygen plus partial pressure nitrogen. And I'll put the numbers in. And add it up. And there's your answer. So this is Dalton's law of partial pressure. The total pressure is the sum of the partial pressures. And the last thing I talked about, now I already gave you in important information, a mole of a compound, its molecular weight of a compound, and the molecular weight is the sum of all atomic weights in a compound, which we use in PV equal nRT. Now, the last thing I'd like to talk about are boiling points. Why is boiling? Because when you boil a liquid, those little bubbles are vapor of that liquid, vapor meaning gas. And when those bubbles come to the top, they release that gas, which has a pressure. And the boiling point of a liquid is when that vapor pressure is equal to atmospheric pressure. Now, the higher the altitude on Earth, the lower the atmospheric pressure. Therefore, you need less energy to make the vapor pressure equal the atmospheric pressure. And because of that, as you go higher up on our planet, the boiling point is lower of that liquid. And I mentioned I used to have friends in Denver, Mile High City, and that's much higher altitude than Chicago. Chicago is at sea level. At higher altitude, Denver, the atmospheric pressure is lower than 1 atmosphere, because 1 atmosphere, 760, is at sea level, which Chicago is. And first time I went there and visited a friend there, they were making some rice or noodles. You could see on the box for Denver, there was a label for the instructions. In Denver, you have to boil it longer, because the boiling point of water is less. Now, for those of you who know geography, if you go to the Himalayan mountains, which are the highest mountains in the world, the pressure is going to be way down, and the boiling point of water will be way down. And with that, I have an important announcement I put out this morning. Let's see if I can get the blackboard. Right here, there's an announcement. And you should check for missing lab scores. As of this morning, all labs that were due last week, those people who put them in on time last week, a couple of you did lab 8 a little late, and I haven't graded them. You emailed me, but check your labs. If you uploaded a lab 1 through 7, I believe, if there's not a score in Blackboard, email me and let me know which ones I didn't grade. Because if you handed it in late, I might have missed that. Next, because the election tomorrow, I have election night lab amnesty program. And what I've done, I've gone back and opened up and made available all the labs from lab 1 until labs that have been due. And you can upload them if you haven't done one. And a number of you are missing some labs. And you have until the 15th of November, 11:15, that's a week from this Friday, to upload your labs, finished labs. And if you do, I will not assess any late points. That's my gift to you, because tomorrow is election day. Now, remember, brave men and women have died so you can vote if you're old enough to. You should vote. I believe Illinois, you can go in the same day of registration, but I'm not sure. By the way, I do mail-in voting, so I voted, I think, last week or a week and a half ago. I've already voted. So don't forget, read this email that you got, an announcement about the missing lab scores and my election night lab amnesty program. And with that, I'm done. And you know what I'm going to do next? I'm going to say, gang gesund. You're welcome, Emily. And I'm going to say, you know, gang gesund means go in health, something my grandmother used to always say to us when we visit her and we're leaving. And after COVID, thank you, Bianca. I always say that. So I'll say gang gesund. And I'll say, before I say goodbye, if anybody has any questions after I say goodbye, I'll stick around for a couple of minutes, and I'll be posting this as a video in my YouTube channel later tonight. With that, I'll say, gang gesund. Bye now. Still there from Granny and the Beverly Hillbillies. Bye.